Um, Welcome everyone to this Bell webinar. We are excited for everyone to attend. Today's webinar is Use Flow in your lab to convert scripts into a reproducible single-click workflow. And today we have a couple of speakers, and our first speaker is Dr. Jhunlyn Lorenzo. And Dr. Lorenzo is a postdoctoral researcher at the Cognitive Neuroimaging Lab, Neurospin, CEA Paris-Saclay, and the Paris School of Economics, École Normale Supérieure. Since October 2022, she has been developing a hyperscanning system using mobile EEG for classroom applications as part of a project funded by IDEE. Her research focuses on designing cognitive paradigms for educational settings, building EEG data analysis pipelines, and integrating neuroscience tools into broader educational research frameworks. She collaborates closely with Ghislaine Diane-Lambert and Stanislas Diane, contributing to interdisciplinary efforts at the intersection of cognitive neuroscience and education. And I just ask that everyone waits and puts questions into the chat, and we will answer questions after both of our speakers. And I will turn it over now to Dr. Lorenzo.
Thank you for that introduction, and thank you, Belle, for inviting us to showcase our pre-processing pipeline for today. And good morning or good afternoon to everyone. Today, I would like to present to you our work here in the laboratory, especially the EEG pipeline, the pre-processing pipeline that we developed, why we need such a pipeline, and give you an overview on how we handle our EEG data. But first of all, I want to introduce to you our Neuroimaging of Development team, which is located in Neurospin and is part of the Cognitive Neuroimaging unit. It is headed by Ghislaine Diane-Lambert. Our team has an extensive experience in developmental research, given that Ghislaine here conducted the first ever EEG studies with babies. And nowadays, we have a wide range of research topics spanning from neonatal and infants EEG studies using high-density EEGs to children and adults hyperscanning studies using mobile EEGs. So through the years, we were able to collect a large data set, and we were also able to perform more complex experimental paradigms, which in turn needs more complex analysis. But we are still facing some challenges in terms of EEG pre-processing, especially because of the unavoidable artifacts. So these are noises caused by environmental factors, physiological and muscle activities, and movements. And these noise are superimposed on the neural signals that is making it quite difficult to isolate and extract those brain activities of interest. And infants' EEG are more difficult or more challenging to handle compared to adults' EEG data because we have shorter recordings, and usually the signals are heavily contaminated with motion artifacts. It's because we can not ask the babies, for example, to just stay still. And there is also a high signal variability due to maturation. Therefore, complex analysis, such as, for example, event-related potential analysis, are more difficult because of the less number of trials and also with the high variability in data. But even though there are standardized pre-processing pipelines that are available, these pipelines were mostly developed for adults. And because of the high variability in the data for the infants, in the infants' data, pre-processing parameters are typically manually set, or artifacts are manually annotated, so making it inefficient when we are dealing with a larger data set. So the solution here is to develop a pre-processing pipeline that is capable of handling various numbers of subjects which automatically defines the preprocessing parameters needed to preprocess each individual data. And this pipeline should be versatile enough to handle broad range of analysis. With that, and with AnaFlow, our laboratory or our team developed and introduced APICE, an automated pipeline for infants continuous EEG in 2022. So it works on this principle that in order to find the artifacts or in order to determine the artifacts, we make a distribution of the voltage values, either in the channels or in the whole recording. And based on the distribution, we determine the extreme values and consider these outliers as artifact and automatically annotate them as bad data. So APICE is a fully automated, flexible, and modular pipeline that can be customized for different analysis. It uses multiple detection algorithm which are sensitive to different types of noise. And here we try to reconstruct the data instead of rejecting the segments or the epochs. This APICE also employs adaptive thresholds. Since we are working on the distribution of the data, this pipeline is also it can also handle a different age group, for example, for adults data. And the pre-processing pipeline works on the continuous data so that in order to retain more epochs later. And the pipeline is available in MATLAB with the EEG integration, and you can please download it in GitHub. Working on the original APICE framework, we are now introducing APICE-Py, which is an M&E Python pipeline, which is also open source and will soon be freely available in GitHub. It is also modular and can be customized for user-specific needs. It supports parallel computing for faster computation, and it annotates artifacts automatically, and it also automatically generates reports for visualization and for quality check. We also include some quality control metrics so that the user can verify the reliability of the data. And now, thanks to Flow, we will have a one-click pre-processing from raw to analysis-ready data. Here is the overview of the pipeline. It is divided into two parts. The first part works on the continuous data, and then the second part works on the epochs data. For the initial processes, it starts with importing the data, processing the EEG structure, and including the electrode layout, annotating, automatically annotating the events, and so on. It also includes processing like re-referencing and baseline rescale. Before we perform the artifacts detection, we apply a minimal bandpass filter using M&E's finite impulse response filter to remove the power line noise as well as the slow drifts. So note that the filter is only applied on the continuous data to avoid the edge effects. And then we try to detect the artifacts and correct them if possible. Then we perform a second artifact detection and another filter if necessary. We can continue with the epoching and identifying the epochs to be rejected or to be retained. And the last step will give us the continuous corrected EEG and the corrected data, such as the epochs, as well as the average responses and reports. Well, let us focus now on the artifact detection algorithm in APICE. So there are three groups of algorithms here, which works based on different sensitivity to noise. The first set of algorithm looks for non-working or non-functional channels. So these channels are the uncorrelated channels, or these channels are uncorrelated with other channels, both in the time and frequency domain. The second set of algorithms detects motion artifacts. So these are the artifacts with abnormally high amplitudes, high temporal variance, and high running average. And lastly, APICE will detect jumps artifacts, which are those abrupt changes or discontinuity in signals. So all the artifacts that were detected are stored in a logical matrix. Well, we have different logical matrix which stores different types of artifacts. We have bad channel and time, or BCT, which is whose size is equivalent to the size of the continuous data, and it stores the location of the samples in each channel across time. Those are the samples that are determined as bad or an artifact. We have another matrix called bad time, which determines the bad time points, which is defined as the time points wherein more than 30% of the channel samples are considered as bad. And we have another matrix called bad channel. So these are the channels whose samples are bad for more than 30% of the recording. We also have a matrix that identifies the bad epochs, or the epochs to be rejected. And lastly, we have an additional matrix for the corrected channel and time. So this matrix stores the location of the samples that are corrected through the process. So here is an example of the visualization of artifacts matrix showing all the bad data, bad time points, and all bad channels. And also the topography here shows the channels that were mostly contaminated. Note that the artifacts information are also annotated in the object annotations and info. And then after detection, we perform a artifacts correction, and which follows the following steps. First, we perform a target principal component analysis, or PCA, to reconstruct those short and transient artifacts. And then we try to reconstruct the segments containing more than 30% of bad channels using spherical spline interpolations. And lastly, we try to reconstruct all the bad channels throughout the recording. So we follow these steps in order to minimize the use of contaminated data for reconstruction. So after correction, we perform another artifact detection, and here is the artifact matrix of the corrected data. So we can see here that there is still some bad time points wherein these time points are longer than our criteria and cannot be corrected. So in order to determine if we're going to reject or retain a subject or an epoch, we have the following criteria. So all bad channels should not exceed more than 30% of the number of channels or electrodes. There should be no bad time in the data, and we can have some bad data, but the corrected data must not exceed 50% of the total data, number of samples. So we also annotate and save the artifact information. So for example, here we have detected some bad epochs and some short epochs. And lastly, we continue with the computation of average response, and at the end, we give the final output, such as the clean continuous data, the epochs, and the averages. We also give the individual log files in order for the user to see the step-by-step process and to check in which type of artifacts are contaminating the data. And we also give an HTML report for visualization and quality checks. It also includes some artifact information and data summary. APICE was evaluated using two different data sets. The first data set is a data set with neonates with an audio task, and the second data set is with 5 months old doing some visual experiments. So we compared here APICE with the extended pipelines, or APICE plus additional reconstruction algorithms. And as you can see here, the standard pipeline of APICE is good enough, and there is no need for additional reconstruction algorithms. APICE was also compared with the standardized pipelines, and we can see here that APICE performed better in terms of the number of retained epochs and SME. Well, in summary, we have introduced APICE and APICE-Pi, which is an open source scalable EEG pre-processing pipeline, wherein it includes automatic artifact detection and correction using adaptive thresholds. It is designed primarily for infant EEG, but also flexible for adult EEG. And APICE is available in MATLAB and in GitHub, and APICE-Pi is also available on demand. So if you are interested in using our pipeline, you can just send me a message. And I would like to thank our NeuroKids Lab team for their support and their help, Anna Flo for her comments and suggestions on APICE-Pi, and Nicolo for his diligent work in optimizing our pipeline. Thank you everyone for listening.
Thank you so much, Dr. Lorenzo, for that great presentation. And now I would like to introduce our next speaker, Roma Shusterman. Roma is the Chief Technology Officer at Bell. He holds a PhD in physics and has over 15 years of experience in neuroscience research, specializing in sensory processing, multi-channel extracellular recordings, and neural encoding decoding methodologies. For the past 8 years, he has led the development of medical devices with a primary focus on EEG acquisition systems and advanced signal analysis pipelines. So we'll go ahead and turn it over to Roma Shusterman.
So just to give a very brief introduction, we have been working at Bell on a flow or a database management and workflows operational system for about last 4 to 5 years. And finally, I'm actually very excited to introduce this feature that we worked for last year, is to allow researchers to containerize their developed analysis, and within a few minutes and bring their analysis from just running notebook or Python and MATLAB just into one click and solution. So flow is a data management structure which receives data EEG recordings from Bell's amplifier Bell System 1. It receives from WISP. It can be also uploaded manually, and the data in flow is organized in studies. Each study included a set of participants, and each file is associated with a participant. And on each file, flow allows to run multiple analyses, which we call workflows. And specifically, when user click on a workflow, it shows what type of analysis allowed to run on a specific file type. For example, on this particular MFF file type, it allows to run 3 out of 5 workflows, because, for example, ERP is not supported because this is not it's a continuous MFF recording, for example. So in terms of workflows, we support Bellevue. This is the application for streaming and visualizing and reviewing EEG data. We support ERP analysis, and we also support two additional recently cleared, FDA cleared analysis like Sorcerer and NEAT. Sorcerer is for source localization of the EEG activity, and NEAT is for sleep staging analysis. And all these workflows were developed under a quality management system in compliance with medical device guidelines and standards. And with all this, as a result of this, their functionality is constrained by the regulatory framework we operate within. And, you know, as an active researcher, I understand that the lack of flexibility required for exploratory research. So to address this, about a few years ago, we introduced support of the Jupyter notebooks. And Jupyter notebooks is a very common and very user-friendly tool where within a same notebook, users can put comments, they can put code, and by comments, they can explain what this code doing, what's their motivation. They can put, they have also visualization of what their code is doing. And this is a very simple and powerful tool that allows to do a lot of flexibility and demonstrations. And it supports rich text elements, some possibility of minimal user interface, and even introduction different functionalities from other languages like SQL or R. So this is commonly used tool by EEG community, but this goes a little bit, or not a little bit, but this actually goes orthogonal to the original idea of developing flow, and which has all this traceability and audit trail, what was performed, how was performed. So, and that's where from here we thought how to merge this all together, and then we came in with an idea to organize this, to containerize this ability to containerize this Jupyter notebooks into workflow. And then with the main goal, once the notebook is developed and a researcher is satisfied with the performance, they can convert it, they can forget about code, and then they will be able to execute this as a workflow without any coding. So from perspective of reproducible research, there are a number of attempts, including all these mentioned here, frameworks like NiPipe, Beads, Neurodesk. Most of them still require some software engineering capabilities to establish this in a lab. And that's where, when we decided to work with containerized notebooks, we thought how to make this indeed very user-friendly. And we come with the following idea. So this is how the general concept of notebooks, our notebooks looks like. So wherever user's code is developed previously, they can put two or more sections, cells around this code. In the first, in the introduction, they should define their parameters as input, output, this perform annotation of parameters or just variables. And these annotations will be used for containerization, and also they will be used for automatic user interface creation. So this set of annotations, and there are a few more, are supported by our Flow API package that we built within Flow. And then at the end, after the user script, they can add, they can decide what data visualization type, report type they want to visualize in Flow. In this example, we just added a simple way of visualizing HTML report in Flow, and we will show this right now. We will show the performance of this on a APICE APICE framework. So from there, once this notebook, few cells are added at the beginning and the end of the user's notebook, then we can come, user can come to this workflow creation tab, and actually by clicking on this new workflow, generate flow, which takes somewhere, it really, time of this creation depends how many dependencies each notebook has, but usually takes somewhere between 2 to 15 minutes. There is a simple interface where user can pick up name, a description of the workflow, choose where from this new workflow will be coming, because in addition to Python notebooks, we also added support to generate to containerize code from any Python script, which can be located on a user computer. And with this simple create button, it will generate a workflow that user can apply later on their files. And after this workflow is generated, it will be allowed to apply this on specific file types. So with this now, let's move actually to the demo. Let me share a Chrome tab. This is this is a Flow, a new version which support this workflow creation, and we will be releasing this release in the next week or two. We're still doing some testing to ensure that it works robust, but the moment we perform release, we can upgrade our flow to all our current users as well. So let's see how easy we can create this workflow for this APICE framework that we just listened to this presentation. So in the notebooks, I just want to show this notebook that so this is to show how to work with the notebooks. We just took main.py file from this APICE folder, and we added her annotation, and we added her and a few additional outputs that we want to for visualization in flow. And then with all these parameters, we just added these annotations that they will be transferred to our user interface. This is also part of the original code. And then we added here two cells. One cell is that because original APICE framework, it works with MNE and FIF format, but in Flow, we mostly work with MFF files. So we did a simple conversion of resulted average ERP file from FIF to MFF. And then we also added visualization within Flow of HTML type of report. Now, when I go to this workflow creation, I can choose this, say, APICE. We have APICE framework workflow. This is from notebook. Now I need to choose the proper notebook. And then I'm starting to create. So here we have details of steps that are going on, and most of these steps indeed takes installation of workflow dependencies. So usually from our runs, creation of APICE workflow takes about between one and a half minute. So it will finish soon. In the meantime, I just wanted to show that we already loaded the original data set that will run this. The moment APICE workflow is generated, we will run this on this input. This is from data provided by Dr. Lorenzo. And so, okay, it looks like workflow. No, it's still functional, it's still building. It should take maybe a few more seconds. Perfect. So the status is available. It's done. Now we can go to study and execute it. And now this APICE workflow, what we containerize, is available as part of workflows that Flow is supported. Once we run here, so we can show this is the setting for the workflows. By default, we used default settings from original workflow, but user can go and modify these settings, including all these parameters. We can modify from true to false or vice versa. So this is what I meant, that we generate a minimalistic user interface where user can work, and then we can choose output names, for example, of the report. I'm saying so that output there, it will output to APICE output directory. The output file will be report.html, and the ERP, one of the ERP will be in an MFF file. And then I can start execution. So workflow right now starts, and takes somewhere about 8 minutes. And again, this is a specific workflow with all the analysis we just heard in the first part of this webinar. So not to wait this, but I already before the seminar, we executed the same workflow on a different participant, and we just show her that this workflow generated this APICE output directory with all these output parameters that user can download. It generated this report HTML, which we can either download or also review within Flow. This is the same. I think these plots we saw just a few minutes ago in a presentation. And we also generated generated ERP from FIF into MFF format. So now we can even review these files, for example, in Bell's supported workflows. And as immediate, we can show this and this ERP of this 256 channels, I think. So that's overall how it works. And you can see that from the moment this workflow is created, users can take and execute this workflow, and all these parameters recorded. One more thing that I wanted to mention, that as part of this workflow generation, user can always download the original source code that is part of the notebook. So user can always have a traceability what code was used to execute specific analysis. So with all this, I think there are a few edge cases that maybe I can address during questions, but we introduced this very flexible possibility to convert coding, established coding pipeline into one-click analysis in Flow with all these benefits of traceability and audit trail.
Okay, that was a great presentation. And we are going to go ahead and take all of our questions in the Q&A. So please go ahead and just put your questions there. I just want to add that along with our panelists today, we have Dr. Peter Mulfees joining us. So thank you so much for being a panelist today. Our first question is, Dr. Lorenzo, do the EEG artifacts change systematically between infant recordings and toddler recordings? Are there guidelines for settings for a piece for each groups?
Well, that's a very good question. Actually, there is quite a big difference between the infants and toddlers data, especially in the movements. So toddlers tend to move more than the infants. So let's say there are more motion artifacts. And also babies, they tend to not blink frequently. So again, we have less blink artifacts than with blink artifacts in toddlers. So there's also quite difference in the maturation in the neural activities as well because of the aging. So we have a different neural signals, let's say neural measures in babies and in toddlers. So for the second question, APICE is an automated pipeline, so we are working on the distribution of the voltages, so and also implementing adaptive thresholds. So there is no need to change the parameters. We're in the default pipeline that we're default parameters that we are suggesting is already enough to do the pre-processing. So since we are working on adaptive thresholds, we don't need to change the parameters from one age group to another.
Great. Thanks for that answer. This next question is about Sorcerer. Regarding the Sorcerer tool, how many channels are necessary to perform effective source reconstruction?
So I think these are two different questions here. Sorcerer was cleared to support 130 and 280 channels reconstruction. This is from the Sorcerer perspective. How many channels are necessary to perform effective source reconstructions? I think this is still a debate in the field, and we believe that more channels is better. There are some studies shows that at least 64 channels required for optimal reconstruction. So I think this is still a debate in the field.
That's a fair answer. Okay, next question. Can we analyze several files at once with this notebook pipeline?
Yes, we can analyze and a user can define multiple inputs and multiple outputs. So this is not a limitation.
And the next part of the question is, can we perform group analysis? Meaning, can I, for instance, generate a mean ERP for several participants?
So this is amazing question. We heard this question for number of years already, and we're currently implementing that average grand average analysis on multiple participants, and will be part of our flow release as well.
Excellent. Very timely question then. Okay. Well, that sounds like all the questions that we have at the moment. Is there anything anyone else wants to ask or discuss after the presentation today?
Maybe, Peter, go ahead.
I can certainly chime in. I think this is amazing. Dr. Lorenzo, incredible work on this pipeline. The visualizations are comforting, to say the least. I know that there is a tendency in our field for all neuroimaging where people need to be looking at their data more. And I think this is a fantastic balance of looking at the data and also effectively cleaning, particularly infant EEG, which we have struggled with on our side as well. I guess my question is sort of a combination that Viral put in the chat, and sort of an extension. So Viral's question was, how hard was it to convert your pipeline from MATLAB to Python? And then I'll take it sort of the one step further, which is there sort of the next step of containerizing these workflows even more so that regardless of what language they're written in, they could be executed on Flow in the future?
Yes, we were discussing this. The only difference the major difference is licensing, because MATLAB requires licensing, and that's where we're working right now actively, how to establish that user can connect their license to allow containerization. That's more, this is a technical, this is a specific technical challenge that we have an idea how to overcome, but that's where delays us from implementing general implementation.
Okay. Dr. Lorenzo, did you see an improvement in speed and flexibility when switching to Python?
So what we did is we optimized it and we tried to improve the MATLAB code to Python code and try to perform parallel computation. So we try to vectorize and do some parallel processing in order to in order to make the functions faster. So in terms of how difficult it is to change from MATLAB to Python, actually, it's a very good question, and it took us some months or year to actually have this default pipeline and a working pipeline, and we are still trying to like improving it, but hopefully soon we will publish some results with the pre-processing pipeline. But nowadays, this is the pipeline we're using in the laboratory. And continuing with what Roma said, we also developed this pipeline for because of licensing aspects.
A question from my side: if using GPU, would it speed up the processing?
Yes,
But
if we can perform parallel.
It will require some more adaptation, right? Because it's
Yes.
Python code.
What we did is we created our own functions because what in our experience the MNI's interpolation functions cannot be used in parallel computation. So what we did is we adapt our old pipeline in MATLAB and convert it to Python and adapt it for parallel computing.
Dr. Lorenzo, thanks for the great presentation. Same to you, Roma. I had a quick question. I don't know if you discussed about the extensibility of your pipeline. I know you've been pioneers in infant and pediatric research over the years, but I wonder if you have any comments on the extensibility of your pipeline for adult work as well, for a lot of researchers that are doing adult EEG, ERP research. What's your thought on sort of the usability of your code towards that work?
Thank you for that question. In the introduction, I mentioned that we are dealing also with adults data with we have some data sets on using high density EEGs as well as mobile EEGs with low number of channels. And we are implementing our pipeline, the same pipeline that we use for infants. And in our experience, it's working well. So it's very extendable and like flexible for all age groups.
And Roma, can you share your quick thoughts on sort of how we're making collaboration easy, particularly for remote labs with shareable workflows and whatnot, maybe at a very high level?
So Flow supports few type of accounts. There is a research type of account where use a lab who owns Flow and Flow server can provide a research type of account to any external user. And a research type of account is actually linked to specific studies. So they can access only defined set of studies. And there is also within the notebooks, we have a shared space. Maybe I can briefly show this. So within the notebooks themselves, workspace, this is a personal space. Share space, this is where all users can access. So this, Vero, I think this together addresses your question, right?
Yeah, no, this is great. And of course, the network architecture of the software in general allows users to collaborate as well in terms of the overall architecture of the flow itself.
Yep. So we have multiple users, multiple roles, but researcher roles, this allows to have very limited access, controllable access, which can be also revoked at the end of collaboration.
Yep.
Right. Well, if nobody else has any more questions or comments, I just want to thank all of our speakers today, and thank everyone for joining us. And we will have this recording up on our website for anyone who wants to watch it again or who wasn't able to join us today. So thanks, everyone.
Thank you.